Welcome to Data Skeptic Time Series.
This is Data Skeptic Time Series, the podcast about how to predict the future based on historical sequential data. Episode number. Most forecasting efforts, at least the use cases I've been exposed to, they tend to focus on short-term predictions. Now, this might be a case of selection bias, meaning I know about predictions on short-term data because longer-term predictions are too difficult in practice. It is almost universally true that accuracy is going to decline the further and further out one predicts. But that doesn't mean long-term forecasts are hopeless. In this episode, I interview Alex Mallen and Henning Lange about the paper Deep Probabilistic Koopman, Long-Term Time Series Forecasting Under Periodic Uncertainties.
I'm Alex Mallen. I'm a student at the University of Washington studying computer science.
My name is Henning Lange. I'm a postdoc in applied math at the University of Washington.
Well, thank you both for joining us today. So the paper we're going to get into, you guys are co-authors on. Tell me a little bit about how you guys got connected.
I actually was the one to reach out to Henning about the work that I saw was going on in Nathan Kutz's lab. He's a postdoc in the lab, and I was interested in the work, reached out to some people, and particularly Henning's work. He took me on, and we got started from there.
So Deep Probabilistic Koopman, Long-Term Time Series Forecasting Under Periodic Uncertainties is the paper. So a couple things to unpack. I guess for background, I'll share that we've been doing our whole season now on time series, and we've covered a lot of the kind of expectations you'd think we would do, ARIMA, LSTM, profit model, and that sort of thing. But I think to the idea of Koopman spaces and that sort of thing and the dynamical systems component might be a little foreign to a lot of people who are familiar with general time series stuff. Do you guys feel that that's the case, or is that just a gap in, my education?
I think it's using Koopman theory in a machine learning context is, I think, a fairly new idea. And I think it's picking up steam at this very moment, kind of, where we actually have algorithms now that can do interesting things. I think it's a fairly new approach, at least in the context of machine learning.
And I would add that I think if you look at this from an outside perspective, outside of dynamical systems, you can see some commonalities with other time series approaches, and it's not totally obscure.
Could you expand on that? What are some of the parallels that'll help people jump into your work if they've got that baseline familiarity?
Well, I think our work is essentially a way to deal with multiple seasonalities in a pretty robust way that allows for long-term stable forecasts, so they don't have any exponential behavior.
Maybe to stay in definitional mode, what is a long-term, specifically, time series to you?
A lot of times forecasts tend to be just a few time steps in the future, but our method is stable for thousands of time steps into the future. It's never really going to explode or anything. So as long as the actual phenomenon obeys that quasi-periodicity, then it's going to be pretty reliable, almost indefinitely.
Well, that makes sense. Let's do another one. Quasi-periodic. Can you give me a rough, at least discussion-level definition of what quasi-periodic is?
Yeah, so quasi-periodic is pretty much periodic, but there might be the case that if your system is driven by two frequencies whose quotient is not rational, you might have a period of infinite, so it technically never repeats, but in most cases it just repeats. So quasi-periodic is almost a careful way of saying periodic.
And I think it has some practical meaning too, in that, for example, there aren't an integer number of weeks in a year, so when you're forecasting, it really helps to have a framework that can deal with that and recognizes that one year won't be the same as the next year because these weeks are not aligned.
That makes sense, yeah. And I certainly have hands-on familiarity with the fact that I can get maybe good predictions for the near-term future with a lot of the standard methods, but those methods might struggle giving me really longer-term predictions. So having some techniques that could do that for me is great. But I come at it with a little bit of skepticism that, isn't the world a dynamic place and it's just going to submit to chaos at some point and it's hopeless. I guess they can predict the weather 24 hours from now pretty well, but I don't think anyone can forecast 7 years in the future. Maybe this is the wrong expectations of systems. What do those boundaries look like from your guys' perspective?
it's kind of the expectation of like what you are trying to predict into the future, right? If you wanted to know the temperature tomorrow, you would probably not want to use a Koopman algorithm because they're kind of almost like opposite of like an LSTM, right? Like, so in LSTM, if you want to do like a short-term prediction, you feed all of the inputs, everything you know in, and then you do a one-time ahead prediction. And for these Koopman algorithms, so we are kind of solving a global minimization problem that also means that it's bad locally, right? I'm not sure if this is a very good explanation, but think about it like this, that we are minimizing the error over the entire time series. And then let's say we've done this and it's September 6th. And you look at your residuals and you realize for September 6th, the residuals, so our error for September 6th is actually pretty large. That means that your error for September 7th is also probably going to be pretty large because we are solving this like global optimization problem. But that means that we can go very far into the future and be reasonably good, but we can't go short term into the future and be very good. That's the catch. Nothing comes for free.
Well, it seems to imply to me that a method like that has a better model of the data generating process, the actual underlying system, more so than one that's taking, I guess you could call it short-term gains, or is really looking at this in a strictly univariate kind of perspective. Is that getting close to the advantages that your techniques bring into the picture in comparison to some of the more vanilla approaches?
So I think the whole idea is that, you said it earlier, like the whole world is chaotic and unpredictable, and we are trying to predict long-term into the future. So basically, the reason why it works for certain systems is there's like this ginormous bodies in space, the rotation of the Earth around the sun. There's like very little chaos in there. It's a very predictable kind of motion, and then like the Earth rotates around itself, right? So we all wake up, I don't know, at like 7 o'clock in the morning because of the rotational position of the Earth, right? And there is like very little kind of uncertainty about this, right? Because the Earth, the next year is also going to be 365 days, the next day is going to be 24 hours. And then this influences a lot of different phenomena. For example, energy consumption, right? Because there's weekends, right? Like we don't, at least in Europe, don't work on weekends. You see those patterns basically in that data. But also, this is a tool, right? And you need kind of the correct tool for the correct problem. If you want to predict the stock market, this is not going to work very well. And it's not going to work well for like intermittent kind of phenomena. But like those phenomena that are like reoccurring, that are kind of like driven by the Earth moving around the sun, the Earth rotating on its own. A lot of phenomena are heavily influenced by those things, and then it works very well for these things. It's like, please don't try to predict climate change with these models, right? Because it will tell you that climate change doesn't exist, right? Because it is stable.
Yeah, so I think it might be helpful at this time to talk a little bit more about exactly how it works, which is it takes basically a vector of sines and cosines with different frequencies and morphs them using a neural network into some nonlinear quasi-periodic functions. And this sort of reflects how we have these perfectly linear systems such as the Earth's orbit of the sun and the Earth's rotation, and how there's these very complicated nonlinear dynamical systems that are driven by those linear ones, such as, people's decisions to turn on the television or whatever. And we're just basically taking what linearity we know about and sort of introducing some nonlinearity with the neural network that sort of represents, on average, how the nonlinear aspects behave.
That's interesting. So there's a lot to unpack in terms of the mathematical processes there. And I don't know that we're going to go through, rigorously all the theorems and lemmas and whatnot. But I think one thing maybe we can take for granted that a lot of the listeners who are familiar with machine learning, they know about support vector machines. And they're therefore hopefully familiar with the kernel method, where you're kind of mapping your input space to some higher dimensional space. And you don't actually use that space. You just kind of do the mapping in order to solve your optimization problem. Is that a fair parallel? Can we talk about this in contrast to something like support vector machines?
It's almost like the complete opposite. I think a very good analogy is Cover's theorem. So Cover's theorem is, I think, from 1965, like very early work or like theoretical work in neural networks. And it's a proof that, so basically, if you have a nonlinear function, you can always basically separate any inputs linearly if you project this into an n-dimensional space, if you have n data points. And there's actually a very nice analogy to Cover's theorem in like Koopman's theorem, which follows like kind of from like the Fourier transform, because the same is true for time series as well. where if you give me n data points, I can always overfit on the training set by just using the Fourier transform, because you're going to have perfect reconstruction because sines and cosines form like a basis in function space. And I think Cover's theorem is like a very good analogy where like you do some kind of like nonlinear projection, you end up in a different space, and in this different space, linear methods just magically work. That's kind of like, I think, a very good analogy. And also, it's kind of also like Cover's theorem where you don't want to project necessarily into a very high dimensional space, right? Because you're at risk at overfitting. And these Koopman algorithms, they overfit very, very, very quickly. So like Alex knows more about this, but like for most experiments, we use like 3 driving frequencies and like a fairly small neural network with like maybe like 35,000 weights or something. So like these are kind of small models because they overfit very quickly.
I think maybe that could be, in some sense, a strength of the approach in that you have a finite number of parameters compared to these models that are coming out now with millions and millions. So perhaps that allows you more control over the range of behaviors of your system, even, of optimally finding things. Is that an advantage, actually, to have a smaller parameter set and smaller network like that?
I think it depends on the problem, right? Like in itself, having a small number of parameters, I mean, it's nice, but because like you have less storage and less compute. But if you have a problem that is highly nonlinear, then you would need more nonlinearity. It's kind of like these Koopman models, they're almost like on rail, where they just keep on doing what they're doing, where like they just repeat and works like surprisingly well.
So what is the neural network learning?
There's 2 different ways to explain it. There's intuitive way, and then there's a dynamical systems way of explaining it. Which one?
Well, let's do both, but let's start with the intuitive one.
I have an explanation. Think about you wanted to predict like a sawtooth function further into the future, which sounds like silly. Why would you do that? But like this is just for illustration. So because a sawtooth has like this like discontinuity and is like very nonlinear, you would need like a lot of Fourier modes in order to accurately model this phenomenon. And this Koopman framework basically allows you to model nonlinearity with actual nonlinearity. So if you look at just like the regular Fourier transform, I don't think it converges for like a sawtooth because you would have infinitely many modes. They decay, but it's like a technicality. It would still be infinite. And in this Koopman framework, well, the sawtooth is only one frequency. So you only have one Fourier mode, and then you basically use this neural network to take the smooth sine function or cosine function and basically make it pointy, make it like nonlinear, right? And what this ultimately allows us is noise robustness. So there's this whole like Bayesian spectral analysis like point of view, which I really like. It's like very underrated work by James and Bretthorst. So basically what they showed is if you wanted to basically extract frequencies from noisy data, then with the more data you get, like your error function becomes more peaked and like higher, basically, and the height of this error valley kind of is dependent on the amplitude. If you have basically the sawtooth and you add a lot of noise, and you have like all of these tiny little Fourier modes with like small amplitudes that you need in order to basically model this nonlinear shape, then they get drowned out by noise and your prediction suffers. But if you have like this Koopman framework, you have only a single frequency and you have your neural network. And in terms of noise robustness, it becomes easier because we only have to infer one frequency. So we can only mess up once. And like all of the small Fourier modes are basically explained away by the neural network.
Yes, I'm thinking of like a Taylor expansion or a Fourier series expansion where you're trying to model either that sawtooth or even a square that's going up and down as you keep adding, and even imagine a little noise in there, and you're trying to refine those, you keep adding more and more terms. Even though we know in the asymptote it's going to converge, it can model anything, it seems that there's an importance to keeping so many terms around. Almost implies we needed a different methodology. Is that kind of part of the motivation?
Yeah, these added terms have like very low amplitudes. If those amplitudes were like just as big as like let's say the sawtooth has like a frequency or like a nonlinear frequency of, let's say, I don't know, 2 pi or something, then you would have all of these tiny little frequencies and they would have small amplitudes. And kind of the small amplitudes get drowned out by noise and then your prediction suffers. But if you have this Koopman framework, you only have one single frequency and then the neural network handles like the nonlinear shape, and then you don't run into the problem of all of these tiny little Fourier modes being drowned out by noise.
Yeah, so then we also want to talk about the dynamical systems perspective of this, the neural network theory. So basically, in Koopman theory, the essence is that you can take any dynamical system, which basically means any time series that we're interested in, and if you do some change of variables, some appropriate change of variables will turn this into a linear dynamical systems in this new space, with the potential of it being an infinite dimensional space in which it's linear. So there is this trade-off, and it's often not very clear how to transform it. But then you can evolve it linearly in this space, and then transform it back into original variables. And so what the neural network is doing is it's acting as that transformation back into the original variables. And what our framework does is it makes it so that we don't actually need to find the transformation into the original variables, because we're assuming that the linear dynamics are just sines and cosines with different frequencies. So we just need to find out how to translate those sines and cosines of different frequencies into the nonlinear dynamics of the thing we're trying to forecast.
The following message comes from Dataiku, the platform for everyday AI. The potential for positive change with AI is huge, but seeing that value is hard. It's about organizational transformation, not just technology. And today's businesses struggle with the complexities of bringing AI initiatives to fruition. That's where Dataiku comes in, bridging the gap between the challenges and tensions present to infuse a culture of working with data and AI every day and at every level of the company, whether solving for the mundane, like automated forecasting, or what is the optimal number of widgets to buy, or undertaking moonshots that push the limits of today's technology to grow your organization and innovate. Join more than 45,000 people worldwide across banking, insurance, pharmaceuticals, manufacturing, retail, and more who are driving exceptional results with Dataiku. Visit dataiku.com to learn more. DATAIKU. Thanks to this week's sponsor, Comet Backup. I've seen people learn hard lessons about backups. I once worked for this company. The CEO had this important presentation and a bunch of Excel files on his computer, and the hard drive went bad. It turned into this emergency situation. I was working around the clock writing SQL queries, and of course, those Excel files had all these pivot tables and stuff. It was crazy to recreate it. Hundreds of person-hours spent. There's nothing more heart-stopping than losing data. Whether you get hit with ransomware, hardware failure, or human error, data loss can be a business-ending event. Comet Backup is a fast, flexible backup platform for businesses and IT providers. It protects Windows, Linux, or Mac, and you have total control over your data. You can back up to local on-prem storage or any of the leading cloud providers. With Comet, you get secure encrypted backup software for computers, emails, databases, and servers. Best of all, Comet grows with your business with scalable per-device pricing. Test drive Comet Backup with a 30-day free trial and get $50 in free credit when you sign up with the promo code DATASKEPTIC. Start running backups in 15 minutes or less at cometbackup.com. That's cometbackup.com, promo code DATASKEPTIC. Interesting. With regard to it being a possibly infinite space, that raises some amount of concern because obviously we can't deal with that infinite space. Are you betting on the fact that most practical problems people have interest in are likely to only require a finite mapping, or is there a need to do some sort of embedding or approximation there?
So I think you get infinite dimensional spaces if you have chaos. And this is going to be controversial for applied mathematicians, but by the definition of chaos, you cannot predict chaos into the future anyways, right? Or like you would only be able to predict it if it's like on like one of those like lobes kind of. You won't be able to basically accurately track your prediction past a bifurcation point. So for example, language looks chaotic. Like if you're trying to model language from like a Koopman framework, it looks chaotic and it just doesn't work. I think it's more like, what is it useful for, right? And it's not going to be useful in every like scenario, because you might have like this chaotic kind of thing, but there's a lot of systems where you can find very good low-dimensional Koopman embeddings. And that's kind of what we should be going after with these kind of approaches.
such as energy forecasting or atmospheric pollution forecasting. These are some of the things we explored in our paper. And one thing, I'm not actually sure about this, I heard that you can't have a linear system that has multiple attractors.
Yeah, exactly. You can't have a linear system with two attractors. So if your nonlinear dynamical system has two attractors, then Koopman theory is going to be difficult to be employed, kind of.
You'd also mentioned that language was one place maybe you wouldn't think to apply Koopman theory. I'm going to put you on the spot because this is sort of out of scope for the paper, but I'm curious to get your thoughts. What if this was part of a two-step process where we took a language model like BERT or GPT-3 and embedded that into their, language embedding space? Would those features be amenable to a Koopman process?
I can share my own experience with modeling basically language with those Koopman approaches. I know that in transformers, some people have used basically sines and cosines to model longer range dependencies between tokens. But after I wrote my first Koopman paper, I'm in an applied math department at the moment, but my master's is in machine learning. So language is a prime kind of application for time series models. So I took this sentiment analysis kind of task. It's movie reviews, and the goal is to classify if this is a positive review or a negative review. And then I used those standard approaches of those word vectors to get a continuous embedding of my inputs. And then I applied basically my Koopman algorithm to it and tried to train it as a classifier. And I got fairly decent results on a test set. But so they were kind of fake, where it learned how to count good and bad words, but it was really unable to extract anything out of the sequence of words, because sequence of not just the words alone, those back of word approaches, but in which order words appear in a sentence is kind of important. And I basically just scrambled the word order, and it didn't influence my score. So I was okay, this looks good, but is kind of bullshit.
Good test, though.
Yeah. I think it's more if you're trying to solve a problem, you want the algorithm whose inductive bias fits the problem. And I think for these language kind of tasks, there might be some kind of Koopman application, but I think it's going to be kind of weird. But then there are different phenomena where the Koopman kind of inductive bias and the Koopman assumptions are actually valid. For example, all of those climate models, basically everything that oscillates, those kind of things.
Well, could we unpack some of the actual data sets that you applied this to and explore where these techniques are useful in real-world applications?
The main comparison that we did in the paper was retrospective with the GEFCOM 2017 competition. GEFCOM stands for Global Energy Forecasting Competition, and it's basically a competition to forecast the demand of energy in the New England power grid for various regions, and to make probabilistic forecasts of them as well. So you're required to give 9 quantiles of the probability distribution for each required time point. It's hourly, the forecast, and for 1 month, but there's a 22-day gap on average between the training data set, which is about 10 years long of hourly data, and the test data set. So this is really an inherently long-term forecasting problem because you have many, many time points in between train and test. And the test data set is itself pretty long. And in this data set, we actually, in retrospect, of course, so there's always some uncertainty about how we would have fared if we were in the actual competition environment and so forth. We looked at the qualifying round and we would have performed number 1 in the qualifying round.
Well, that's fantastic. What do you attribute that success to? Is there an aspect of the methodology that the other techniques being applied simply missed that you were able to capitalize on?
So the other approaches do very, very similar stuff. All of these models, they look at the day of the week, the month of the year, the hour of the day, and then basically try to predict based on this kind of information. And this Koopman stuff does the same thing, right? So this vector of sine, so we probably have, for those experiments, we used 3 frequencies, right? We had yearly, weekly, and daily. And we also trying to map basically from hour of the day and day of the year, and we add day of the year, day of the week, and hour of the day. We're trying to find a mapping to energy consumption. Our approach is just smooth. So it's modeled by sines and cosines, where the other approaches they're discrete. And yeah, we can use basically a neural network to solve our optimization problem for us. I think that's part of the reason.
And one thing that smoothness allows us is you don't need uniform time points. So if you have missing observations or your data was just not recorded on a regular basis, you can also use this. And that also means that your predictions don't have to be a certain number of time steps in the future. You just plug in the time value and you get the prediction at that time.
Which is very nice, kind of like you don't need to do any time stepping, right? So if you want to know the energy consumption like in 2 million years, it's computationally just as expensive as in 2 weeks, kind of, because you just need to plug the time in and you get your result out.
Is there any way a user can get some feedback about, I don't know, like a confidence interval or something along those lines? While I might anticipate your 5-year forecast could be viable, I also might feel more confident if the error bars were a little wider or something like that. How can a user inspect the forecasts?
So in the end, the optimization objective that we are maximizing is the data likelihood. You get like a full distribution out and you can evaluate the likelihood of all of these different points. And that's kind of like this like intrinsic kind of uncertainty about like how many people got up on this Wednesday at 8 o'clock and actually drove to work or something. But then there is a second aspect where we know technically the error bounds, but the error bounds are very, very sharp and oftentimes like not useful for prediction. But we are maximizing the data likelihood, so we get like a distribution for every value for every point in time.
So for example, one of the outputs of the neural network is it could be the standard deviation of the distribution, and that is again assumed to be quasi-periodic. So it's not going to increase with time on its own. Your uncertainty is going to stay roughly constant except for with the periodicity. And I think that there's room for maybe generalizing this for phenomena that might not be as quasi-periodic as our model assumes, and allowing for what you said, which is we want the confidence in the future to be smaller than the confidence now. But currently our model doesn't give us that. But there's a lot of scenarios where it actually seems to, in a reasonable picture of the future, seems to hold as a pretty valid assumption. So for example, atmospheric concentrations of nitrogen dioxide, I think it was we were forecasting, that's a pollutant. And a lot of times it drops down to 0. So we model the distribution shape with a gamma distribution because it's non-negative, but it's close to 0 a lot of times. And we don't really see any reason why this should change super significantly in the foreseeable future. So there are still problems in the hypothesis class that our model has.
It's a stiff model, but there is a lot of interesting kind of phenomena that you can model with this, right? So energy consumption, like atmospheric chemistry, kind of like predicting like air pollution. So we tried this on, like in the original paper, I did like human gait. It was a subject and he had a phone with an accelerometer in his pocket, and while walking is also like a cyclical kind of left foot
It'll show up in the accelerometer on your phone, I know firsthand.
Yeah, we modeled that with that. You need to like be a little bit tricky to get like kind of decent results, but yeah.
Well, yeah, let's maybe unpack one of the other use cases. You were talking about climate models. Could you talk a little bit about how well the techniques have applied there?
So I think just need to be careful, right? Like, so we were talking to Christoph Keller, he works at NASA, and they have like those ginormous kind of climate models where like you have a bunch of PDEs and it's very expensive to solve. And kind of one problem that they have is if you want to integrate your PDE out, you need kind of like an estimate of like what does it look like right now. And this model, I wouldn't use this model just for climate change without using like those PDEs. But like I think one potential use case would be you use this model to get basically like an estimate of like the pollution concentration right now. And then you use like the big NASA model to condition this output basically on, well, there's a wildfire going on in the Pacific Northwest, right? That's another thing. Like those Koopman models, it's kind of difficult to condition them on like what is happening right now because they're kind of on rails and they just keep on doing what they're doing. So I think one potential use case in like climate modeling or like pollution modeling is that you use this model as like a initial guess of like the initial conditions. And then you use basically one of those big models to incorporate the knowledge of like there's a wildfire going on in the Pacific Northwest. But like just this model is kind of dangerous to use because you are assuming that everything stays stable, right? So for example, sea surface temperature, it's a very big nonlinear oscillator. And if you apply this to sea surface temperature, you get like, it looks very nice, but it's going to just stay flat, even though sea surface temperature is rising. There's a danger there.
Well, for someone who's dealing with maybe a complex time series problem of some kind, where it's not just a univariate analysis, it's a real evolving system, that are interested in techniques like this, do you have any thoughts on the Litmus Test they can use to decide if this is a technique appropriate for asking questions in their domain?
One thing that we did in the paper to ensure that our forecasts were reasonable was to basically take, I think this is called backstepping by some other people, or back forecasting, I forgot exactly. So you just take part of the training data and forecast that data, but, leaving out that data from your training in this example, just for the litmus test. And you take those observations and, for example, if you have a Gaussian, then take the z-score of each observation and see if it forms a normal distribution centered at what you want it to be, centered at 0 and with a standard deviation of 1. I think I should explain that better. One thing we did a lot in the paper to check if our forecasts were valid was we took maybe 70% of our data and trained on that, and then forecasted the remaining 30%. And then on that 30%, we looked at how the observations were distributed in relation to our model's forecast of it. So if you take the quantile of each observation within the forecasted distribution of that observation, the quantiles should, in theory, have the appropriate CDF. So
it's basically cross-validation, right? So you leave out a little bit of the data and see if your predictions are good. And you have a domain expert that knows about certain properties of the system, right? So most people probably know if the phenomenon they're trying to model is a nonlinear oscillator. If it's not a nonlinear oscillator, this approach would probably not be a good choice. But if it is a nonlinear oscillator, it could be a pretty good choice. Also, another data set that we are actually kind of exploring right now is data from geosciences. We are talking to someone from the geosciences at UW, and I'm not a geoscientist, but I think they're trying to predict the moisture of soil, because in either ways, if your soil is very moist or very dry, you have increased risk of earthquakes. And there's one data set which is actually kind of interesting. In California, where El Nino happens, it rains a lot, and it kind of is like a battery. And then over the next 5 years, this moisture battery kind of gets drained. But then there's this other cycle of this yearly cycle where there is more precipitation in the winter compared to the summer. So you have two frequencies, right? You have El Nino and you have a yearly cycle. And so it's probably a nonlinear oscillator. So it might make sense to use it, but then you probably want to do cross-validation or something, like a technique where you make sure that your predictions are accurate. And then again, it's very easy to overfit these models. Very, very easy. So make sure you're predicting on the test set.
Good advice. Could we touch on one of the other categories, that of neuroscience? A very famous nonlinear system. The brain seems to be a pretty complicated machine. How useful can this technique be for a neuroscientist studying the brain?
I think that experiment was not really looking at the nonlinear oscillations of the brain. So we had 10 repetitions of a stimulus was presented to a mouse. This wasn't an experiment done by us. It was an experiment done by the Allen Institute for Brain Science, but they have publicly available data for all their stuff. It's great work. And we looked at the mouse's response to these 10 repetitions of this video, 30-second video, and it was 10 repetitions in a row, so it was all continuous. And we basically said that the frequency was this 30-second video length. And we basically able to show how our model can pick up the changes in response throughout the video.
The mouse is presented with a periodic stimulus. And that's why we know that the signal is periodic. If you wanted to use this for neuroscience, because neurons are kind of nonlinear oscillators, you would probably want to do kind of short-term kind of analysis. You could use this, for example, to estimate the current firing rate of a neuron.
Yeah, so I would say that experiment that we did there was not so much the nonlinearity of the brain, but more so just showing how the responses fluctuate throughout the stimulus presented to that mouse.
So I noticed the paper mentions this is all implemented in PyTorch. Can you talk a little bit about the development and also if it's available for people to look at and maybe work with?
Well, actually, the original code was from Henning's paper in, I think, November in JMLR on sort of the foundations of this technique. There's 2 GitHub repositories, one with experiments that we did for the most recent paper, and then another one which is the source code for an open source Python package available on PyPy called dpk-forecast, which just allows you to use our forecasting technique.
Very cool. Well, that's as simple as pip install then, I would guess, right?
Yep, as simple as pip install.
And what's hello world look like if someone wants to put this to use?
A sign of any frequency, or like apply a nonlinearity to a sign, shove it in there, and it should like give you the prediction of the sign, kind of.
Very cool. We'll have a link to that in the show notes so listeners can check it out.
Yeah, and there's an example Python file of how to use it in both GitHub repos.
Well, to wind up, I'd love to hear about where you guys envision this line of research going in the future.
So I personally think there is tons of application in the sciences. So there is like geoscience, have like everything that's kind of where like the rotation of the Earth around the sun kind of influences your phenomenon. All of these kind of things are oftentimes nonlinear oscillators. And I kind of think that this is actually a very good approach for like those scientific applications where you know that your phenomenon is a nonlinear oscillator. I don't think that this approach is gonna be used like as a replacement for LSTMs in, let's say, language modeling anytime soon, where like the inductive or like the phenomenon that you're trying to model just doesn't fit the inductive bias of the method, kind of. Oh, and it's like another application that we did is like imaging. So like crystalline imaging, you have like periodicities in like molecule structures. And that's also like whenever you have something that just repeats itself, like kind of like periodic, this is an appropriate approach, kind of. It's not artificial general intelligence.
No, but I see what you mean when you say the applications in the sciences. You know, everywhere there's these kind of isomorphic, iso whatever properties. You know, the source code of the universe seems to be the same everywhere. So as you spread out and study some big field of like a crystal or something like that, it's the dynamics are certain to have these types of patterns.
Oh, and also probably one of the biggest applications we kind of left out. So Koopman theory comes out of fluids. So a lot of fluid flows are also very big nonlinear oscillators. But then with fluid flows, you get to chaos very quickly. But for non-chaotic kind of fluid flows, this is a very good technique as well.
Alex, how about your thoughts?
I think, yeah, in general, it's just good for the sciences. I can't think of any further specific applications. I know we're going to work with NASA some more to try to improve their atmospheric pollution forecasts by sort of creating a more robust priors, such as the traffic forecasts that they use and so forth, to try to improve their model. And this is one specific case of how we're going to try to use our forecasting method.
Well, fascinating. Exciting to see it put to such good use. Well, thank you both so much for taking the time to come on the show and share your work.
Yeah, thank you.
Thanks a lot for having us.
That concludes another installment of Data Skeptic Time Series. Our guests today, Alex Mallen and Henning Lange. Thanks to our sponsors, Data IQ and Comet Backup. Myself, Claudia Armbruster, as associate producer, Vanessa Bly, guest coordinator, and our host, Kyle Bullich.